Okay, so this is a video to have a look at a number of things you might be expected to do with mass spectra and relative atomic mass. I'm going to start off by drawing just like a very simple mass spectrum here. Of course, the y-axis we have our percentage abundance, and then our x-axis is our mass to charge ratio. And I'm sorry I haven't drawn it exactly right, but let's imagine that we've got two peaks of equal height. One's at 79 and one's at 81. And if we were to imagine sort of sending 5 particles down into this mass spectrometer, sorry, 10 particles, let's say 10 particles. Okay, so 10 particles in total, and what we're actually sort of going to be wanting to do is try and work out what is the average mass of these particles. And the way I've drawn it to try and make things a little bit more visual, easier to see. So we've got, in this case, 5 particles that have a mass of 79. So we're going to say 79 times 5, and we've also got 5 lots of 81. Okay, and our total number of particles, of course, therefore is 10. And of course, if we average that out, I mean, you don't need to use a calculator. You should work out that that comes up with the number 80. Now, of course, in reality, we're not going to be sending down 10 particles, and what we're looking here is a percentage. So we can do the same sort of thing with the percentages. So we go for 79 times 50% and plus 81 times 50%, and that's equal to, again, 80 when we divide by the total. In this case, the total is 100. Okay, so total is 100, but we can actually sort of do this even simpler by saying, right, well, rather than sort of working with percentages, why don't we convert those percentages into decimals? So of course the decimal equivalent of 50% is 0.5 plus 81 times 0.5 again, sorry. And again, that's still going to be 80. Okay, so this technique here, I mean, if you actually put in the decimal values, it just makes things a little bit simpler, and it's going to make things a little bit easier later on as well. Okay, so working out the relative atomic mass, if you're given the abundances, all you need to do is add up the percentage sort of multiplied by the isotope in question. Okay, pretty simple. So that's that. We're going to have a look at something else. Okay, so let's imagine we have another spectrum. Okay, let's do the same sort of thing here. We're going to go 35, 37. Okay, and of course on our side we've got our percentage, and this is our mass to charge ratio. And in this case, I mean, you'll probably be familiar with this. We're looking at the mass spectrum of chlorine atoms. Okay, so in this case, we want to work out, well, what's the relative atomic mass of chlorine using the figures that we've been given here. If we know that the chlorine 35 has an abundance of 75%, roughly, and the chlorine 37 has an abundance of 25%, roughly, then we can punch those in and do the same thing. So it's 35 times 0.75 plus 37 times 0.25. In this case, of course, when we punch these through, we get 35.5. Okay, so not too bad. This next bit is where it's going to start getting interesting. Okay, so we've had a look at the working out our relative atomic mass given our abundances. Now we want to sort of work at this from another angle. What I'm going to do is actually rewrite out, I'm going to pretend like we actually do know some of the information that we don't have, and I'm going to sort of write that out, and we're going to sort of punch back in and see if we can sort of work out how we can sort of approach this as a problem. Okay, so I've got my equation that I've written out from before. Now let's imagine we begin with a question. We've been told that there are two different isotopes of chlorine. One is chlorine 35, one is chlorine 37, and the relative atomic mass is 35.5. Our job is to come up with these other numbers. Now we can rewrite this, okay, of course, is saying, well, if we don't know what these values are, we can substitute them for some letters, for example, and do a little bit of algebra. So we can say 35 times x plus 37 times y is equal to 35.5. And then the next thing we're going to work out is, well, okay, well, is there anything else about x and y that we know? And of course, in this case, we do know that the total of all of these values, in this case, so 0.75 and 0.25, that's always going to add up to 1. So the total of x and y together, x plus y, is going to be equal to 1. And therefore, we can sort of rephrase that saying, well, okay, therefore x is equal to 1 minus y. Okay, and we can now substitute this equation into this one here. Okay, so I'll rewrite this one down. That's 35 times 1 minus y plus 37y equals 35.5. Okay, and then we've got 35 minus 35y. This is expanding the brackets, plus 37y is equal to 35.5. And then we can collect together some of these terms. So we've got a 35 here and a 35.5 here. So we can take 35 away from both sides. 0.5, excuse me. Okay, and then in this case the y terms, we've got minus 35y and plus 37y, so that leaves us with 2y, and therefore we can say that y is equal to 0.25, and of course matching our y back up, where are we? Okay, so the y is matching to the 37, so we can say that 37 chlorine, the abundance of that is 25%. And of course, if that one is 25%, it doesn't take much for us to say, well, therefore the other one must be 75%. Okay, so that's pretty easy, not too bad. If you practice that a couple of times, when you're going to be doing this on exam papers, it's likely that you're going to be looking at doing this with slightly longer numbers, okay, because otherwise you could just end up pulling the values straight off of the periodic table. So we'll do an example working with some longer numbers. Now, I'm actually going to sort of work through this as we go along and show you where you can pull some numbers up to have a practice on this yourself. So let's just clear this away for the moment, and yeah, okay. So if you pop into Google something along the lines of periodic table, relative isotopic abundances, I'll leave links to these on the video if I can. The first link that comes up here is actually a pretty good one, isotopic or isotope abundances for all the elements in the periodic table, and that one looks like this. You get a sort of a page here with some simple information, and this is going to actually give us some answers for the questions that we've just been looking at. And what I want to do is go through here and find really some examples where there's only two isotopes. So we've got iridium there, vanadiums coming up. I'm going to stay away from the ones where there's only a tiny percentage of 1, just to begin with. There's the chlorine, and you notice already actually it's not exactly 75 and 25. You know, there is a slight discrepancy here, so that's where these more precise numbers are going to come in handy. So let's have a look for copper, because I've got that open in another window. So here we go. We've got two isotopes of copper, chlorine 63 and 65, and you want to actually, this is going to be the answer that you're looking for. You want to come up with a way of actually sort of working out what the accurate mass of these particles is going to be. So 63 and 65, if you sort of put those numbers in, you're not actually going to get the values that we've just got here. So again, if you type into Google isotopes of copper, you should be able to come up with, again, good old Wikipedia gives us a more accurate mass that we can work off with. I'm going to just maybe take these numbers with 4 decimal places or something like that. Okay, so let's take these numbers through and go back to the board. There we go. Okay, need a new layer. There we go. Okay, so some isotopic information on copper. We've got copper 62.9296, and then there's copper, that's copper 63, and then copper 65 is accurately is 64.9278. Of course, think for a moment to yourself, well, why is copper 65 not exactly 65? I mean, we're not taking an average value here. Of course, the answer is, well, yes, we are, because we're comparing this now to, we're still on this scale where 1 really is a 1/12 of the mass of carbon-12. It's not the mass of 1 proton. Okay, so, and of course, you may be aware that the mass of the proton and the neutron, for all intents and purposes, they're close enough to being the same, but they're not exactly the same. So if we're going to be doing this exactly, then we need to be using some exact numbers. Okay, so let's, the other piece of information we need, which I also got from the same webpage, is the atomic mass of copper, relative atomic mass of copper. Okay, is equal to 63.546. Okay, so we're going to write out our equation in the same way that we did before. Okay, so slightly more accurate numbers. But we're going to use the same process. We can still say that the total of these numbers, x and y, is still going to be 1, and therefore we can say that x is going to be equal to 1 minus y, and substitute that in for this first term here. Okay, and then we're going to expand the brackets here. Okay, next thing, let's collect the terms together. So we're going to take 62.9296 from both sides. So that's 0.6164, 0.6164. Run off the edge there, 6164. Okay, and then collecting the other two terms together is equal to 1.98. Let's go for 1.998. 1.998. Okay. Okay, so we need to divide by 0.6164. Okay, and then we need to divide through by the 1.998 so we can get y on its own. So that's 0.6164 divided by 1.998 gives us 0.3085. And that's a 3085. So effectively we're saying y is 30.85%. Okay, and the y in this case is the copper 65. And then of course the last thing is to take 30.85 away from 100. So 100 minus 30.85 is going to be 69.15. Okay, the 69.15, that was the X, which is the copper 63. So that's 63 copper, and then this one is the 65 copper. Okay, then you go back and have a check. So hopefully we're going to see something along the lines of sort of 69.15% when we go back and check. So here we go, 69.15% and 30.85%. There we go, perfect. Okay, and that's also in the other, there you go, in this case where it says 69.17% and 30.83%. You know, if you're getting tiny discrepancies there, of course, it's going to depend on where the exact values are coming from, but that looks good. Okay, then the very last thing you have to be able to do is then be able to sketch or come up with the ratio of some of these peaks to each other. So let's go away from the longer numbers and just go back to these sort of simpler numbers and go back to, for example, our chlorine. So we have our chlorine 35, 35 chlorine. We know that that is 75%. We have our chlorine 37, and that's 25%. And okay, so all you need to do basically is we're looking for the ratio of these numbers to each other. So it's going to be 75% divided by 25% gives us 3 to 1 as a ratio. So if you were to sketch that out, you've got something that's trying to make sure this one's about 3 times as high, and this one is at 35, and this one's at 37. Thankfully this last bit is a bit simple to keep track of. Okay, so we've got 3 things that we had to do. Calculating atomic mass, relative atomic mass, pretty simple. Predicting the peak ratios, not too bad. And the calculating the abundances, it does trip people up potentially with the slightly longer numbers, but if you keep working and practicing using the sort of numbers in sort of simple ratios, you can, and then you can build up to sort of working with slightly longer series of numbers to get more precise values.